Here's another image, and now we're zooming in to just an inner 30 or 40 arc seconds. So this is like 1 arc minute across here. That's only about the size of a big crater on the moon in terms of angle. And it looks like you're seeing a spiral. Like stuff might be spiraling into the center of our galaxy, which is right there. And then a better image shows, yeah. So these arms are not spiral density waves like we talked about before. This looks like material that's actually going in to Sagittarius A, the strongest radio source in the sky. So there's very strong radio radiation coming out here. That's telling us there's a lot of free electrons that are spiraling pretty viciously around the magnetic field line. So why is there such a strong magnetic field? And where's all the energy coming from to ionize all this gas? That's the question that you'd normally ask once you see this. So the next clue, there's Sagittarius A in infrared light. So the next clue came from UCLA astronomers. Remember, I got my PhD at UCLA, so some of these people I knew. Andrea Ghez and her group, and this is now 20 years old, and what they did is they took very careful photos with the Hubble Space Telescope, and they showed that there are stars there that are following orbits like this. So the stars were moving fast enough that you could literally see them undergoing proper motion. So 1995 to 2002, so here's 7 years worth of orbital motion. Remember now, this is like 28,000 light years away. And this is like half a degree. So to have these stars move that fast, did I say a degree? I think that's an arc second. I'm sorry. Arc second. So you need the Hubble Space Telescope to see down to that kind of angular view. Because this square here is this whole picture here. Look at this guy. Look at the orbit that this SO16 follows. Deep plunging orbit all the way into there and then zooms right back out. This is telling us that the mass around which these guys are orbiting is a very concentrated mass. And when you use Kepler's laws and you look at how fast they're moving, and when we know how far away the center is, so that gives us the other orbital parameter, and you calculate and you find out that, my God, the mass that's swinging these stars around is like 10 million times the mass of the sun. And yet you can't have stars that are anywhere remotely close to that kind of mass. Stars bigger than about 150 solar masses will actually have so much luminosity they'll literally blow their outer envelope off immediately. They can't be contained. Their Eddington limit has been exceeded, and you won't have stars that last at all for masses like that. In fact, the only way to have that much mass in that tiny a volume is for it to be a black hole. So this was really nailing the case that we have a giant black hole in the center of our galaxy. We'll do the whole active galaxies and black holes story next week, but and so it's not at all surprising we have a black hole in the center, but it was only an inferred probability until this work, which really cinched the case. So how did the Milky Way form? That's really more properly a subject for cosmology, because all galaxies, especially all big galaxies, formed right after the Big Bang. And so I'm going to save most of that for later. But just very briefly, protogalactic clumps, or smaller galaxies, where star formation had already begun, fell together, or to use the technical term, smushed together, and became the central bulge of our galaxy, and then more slowly and gradually, intergalactic gas fell in, hydrogen gas, fell in from farther out. It fell in with some angular momentum because it was also feeling the pull of, for example, the Andromeda galaxy. So it didn't fall straight in, it fell in with some sideways motion, and that's why it settled into a disk rather than just falling straight to the center. Okay, and then globular clusters formed during the proto-galaxy stage when collisions of fairly big clumps of pre-existing stuff was happening. That's the kind of environment we need in order to make globular clusters. And all this happened easily within 1 billion years or so after the Big Bang. It's the same for most other galaxies. So the evidence for the formation sequence of our galaxy comes from work done by Walter Baade in the 1950s. So he discovered something really interesting. Stars with so-called metals, remember astronomers use this loose term called metals to mean anything that's heavier than helium, were all in the disk. So those stars were called stars of population 1. Stars with high metallicity were called population 1. Stars he found, there were also stars he found that had no metals. Those he called population 2. So to divide the stars between those that had metals and those that didn't wasn't particularly informative, and calling them Pop 1 and Pop 2 wasn't particularly informative. What was informative was where these stars are found. So I already hinted at it when we looked at the Andromeda galaxy, but the big clue is that the Pop 1 stars, the population 1 stars, the ones with metals, they're all found in the disk. You don't find any of them out in the halo. The Pop 2 stars, they're all, well, most of them, the large majority of them, are in the halo, in the central bulge, in the globular clusters. They do not dominate the disk. So the story that emerges is that the bulge formed first out of pristine material, fresh from the Big Bang, and thus had only the elements, the chemical elements, that emerged from the Big Bang, and we'll justify later why that's only hydrogen and helium. Lithium, beryllium, boron, carbon, oxygen, nitrogen, sulfur, etc., all the way to uranium. All of those are only formed later inside stars. Out of the Big Bang came just 2 elements, hydrogen and helium. So, age dating about 70,000 red giants across our galaxy confirms this general picture. In the video link, you'll notice how there's more stars, core stars in the central bulge. They make up the very old stars, which form first, then the flattened disk above and then below, and then we call those the intermediate age disk, and the youngest stars are the closest to the center plane of the galaxy. So there's that. Extreme Pop 1 are stars that are very, very tightly fit on a flat plane. And of course there's a gradation here between. They're not really that distinct from each other. It's a whole distribution. All right. Well, that takes us to the end of our Milky Way chapter. So what we're going to do next week is we're going to talk about galaxies in more generality. So now we've studied a spiral galaxy up close and seen the interstellar medium, and we have a hint now about how galaxies evolve. The central bulge forms first out of clumps of gas and stars that existed right after the Big Bang, stuff that formed early. And the stars, of course, that are in that early stuff are already so tiny and so dense that when they collide together, the stars themselves literally don't collide. It's only the boundaries of the system that overlap, and the stars themselves are just far too tiny to do that. And then that makes the central bulge, which is now made of old stars, stars that date back 13 billion years or more. And the disk only forms later, and then as the disk gets more and more settled by gravity, gradually it gets dense enough that you can have star formation going on in it. But even there, it's tough, and what really helps star formation to happen in the disk is these spiral density waves. Now, I didn't really explain what a spiral density wave is, but the orbits of the stars in our galaxy are not perfect circles. They are not very elliptical, but they have some ellipticity, and we remember one of the properties of ellipses is that the stars will, the orbits, the things in the orbits will move more slowly when they're far away, and they'll move quicker when they're in close. So what that means is that the stars will slow down and tend to congregate, and there'll be a bit of a traffic jam, a bit of a traffic jam in the outer parts of these orbits. And when those resonate with each other and form a larger concentration, I guess I'd say, then we have the ability for the gravity there to pull stuff together and make stars. So star formation is enhanced by these spiral density waves. All right, well, I'm going to end it here. So that's almost an hour, and that's most of our hour-and-a-half class. So what I'll do is I want you to listen to this tomorrow. Play it on YouTube. I'm going to try and get it uploaded to YouTube before class starts tomorrow at 9:30. And so from 9:30 to 10:30 or so, I want you to be watching this lecture and watching the slides. And then for the last half hour of the class, and then we'll get together on Canvas and you can ask me questions. All right.